This is going to be lecture 2, and we are starting with preferences and utility functions. So I think we touched on preferences in the previous video and how it is constrained by our opportunity costs on an individual level and on an case level or case to case level. So for instance, every single act that we basically undertake could have two possible directions, meaning that we can do either that or something else or a variant of something else's. So end of the day, everything we do depends on those opportunity costs, and we do a measure, a weighting of which thing to do, and we just do whichever suits us the most given the constraints that we have, and that is essentially what becomes our preference. So that being said, we are going to start with that today in this video. To be honest, we already started. There's a nice diagram for the previous one. Goods, firms, households, goods and services don't need. I think we were directed to 1.17. This is the one. So let's just do a bit of reading, and this should have been on the first lecture. I thought in this particular video we would start with lecture chapter 2 in general, but why not? Suppose that the demand function of the commodity in problem 1.13 changes to UD. Okay, so this is the formula. We are yet to learn this formula, I guess, but this is essentially straight line formula. So this is essentially straight line formula. We have your y equal to mx plus c, so it changes to this. Define the new market demand schedule for the commodity. I don't think we have studied market demand schedule. Number B is draw the new market demand curve on a figure identical to that point in problem 1.15, which we have not done. And number C is what are the new equilibrium price and quantity for this commodity. Is this solved? So this is not part of the question. This is part of the answer, I suppose. Is it? I think we'll come back to this. We'll have to return to this. But more or less, we are going to start freshly all over again for chapter 2. Demand, supply, and the equilibrium and overview. We have different things that we would like to understand from this. So let's just read through some of that. The individual's demand for a commodity. I think this is going to set the base for demand function. Demand function is downward sloping, makes sense. Demand function depends on price and quantity. Supply function depends on price and quantity as well. The law of negatively sloped demand. Shifts in the individual's demand curve. What factors could shift that demand curve upward or downward? The market demand for commodity. Okay, we are going to here we have the formula is a straight line formula. Then we have, I'm going to shut down the front camera for a bit. The single producer's supply of a commodity. We have finally the supply curve as well. So we are also going to set the foundations for supply curve here, like mentioned here. Then we have the shape of the supply curve. Okay, shapes in single producer's supply curve. Again, we are not doing the general thing that we learned in chapter 1. We are doing the specific or particular case, the one that was not general. The market supply of commodity. Okay, equilibrium is this place where we have equilibrium stuff. Types of equilibrium, apparently we have many different variations of equilibrium. And then we have glossary, and that's basically this chapter. Cool. Um, let's start with this one. I guess I can have my thing back if I'm ready. Okay. I'm not going to watch this here because the sound is going to screw things up for me. What I'm going to do is go on a separate laptop that I have in front of me and start here. So this is going to be much of the lecture today. Much of the stuff from this video. So what I'm going to do is I'm going to follow this lecture through, try to follow this through to the best of my possibility, um, and see what useful things I can come out. What useful thing I can what useful thing I come across is going to be the challenge, and one way to get help in that regard is reading through the notes that I already have. So this is for instance the note. Starting with introduction, the lecture will focus on foundations of demand curve, consumer choice, and preferences. So again, harking back to the things that we mentioned, consumers choice and preference, we're going to deal with preference here. The core concept is utility maximization. Utility maximization is okay, combining consumer preferences and budget constraints. So we are going to learn that. Then we have model of consumer decision making is based on utility maximization. The two key components: consumer preference and budget constraint. Consumer preference deals with what people want. Preference is basically what people want, and constraint is what people can afford. And opportunity cost is basically the road you did not take. The model will explain how these components lead to the demand curve. Step 1 today: preferences. How model people's test. How to model people's test. It's basically what she's going to start with. Also today we are going to learn utility functions mathematically representing preferences. We are going to learn how to represent preferences but mathematically. How is that going to be? I think that is going to be done through the straight line demand curves. Yeah. Yes, this one is going to be perfect. So this is a preference. So for instance, in this place you can want this, you can want this point, you can want this point. For instance, at this place you have 1 unit for $7, or you could be asking for 2 units at $6, or 3 units at $5. So this costs you 15, this costs you I think 12, and last day this costs you 7 for 1 unit. So this is what you are going to contend with. So for instance, uh, how many chocolates can you have? You can have 3, and it's going to cost you 15, or you can have 2, which is going to cost you 12. So yeah, preferences and utility functions, we are going to learn that, and next time we are going to learn about budget constraints, limitations on consumer choices. Today's focus is on unconstrained choices, assuming no budget limitations. So what we're going to learn today is that we have no budget limitations. Okay, budgetary limitation. And then we have preference assumptions. Consumers can compare and rank any set of goods. Completeness, transitivity. If A is preferred to B and B is preferred to C, then A is preferred to C. Okay, transitive nature. Okay. Then a non-station assumption: more is better. Non-satiation, satiation. Non-satiation assumption: more is better. Consumers always prefer more of a good to less. That might be objectively true. And then we have the assumption is crucial for people. Assumption is crucial for power of economic model. Okay. Indifference curve, graphical representations of consumer preference. How do we model consumer preference? I think with the demand curve, show combinations of goods that provide the same level of satisfaction. Mm-hmm. The consumer is indifferent between them. Okay. Properties of indifference curve. We're going to learn indifference curve early on. Indifference curves slope downward. The indifferent curves never cross. Utility function, mathematical representation of consumer preference. I think I might have to play the video. Um, Play the video, and that should be covered under fair use, because I don't see any other way I can get through this. Utility function, mathematical representations of consumer preference. Utility is an ordinal concept, ranking of preference, not absolute values. All right. Okay, so this is like how do we model our preference? We model our preference through indifference curve. Okay, so model preference with indifference curves, which would be a variation or version of supply or demand curve basically. Then we have by 11 minute we have utility function, mathematical representation of consumer preference. Utility is an ordinal concept, ranking of preference, not absolute values. Ranking of preference, not absolute value. Marginal utility, the additional satisfaction gained from consuming one more unit of good. Diminishing marginal utility, additional satisfaction from each successive unit of a good decreases. Okay. The additional satisfaction of such each successive unit of a good decreases. Okay, that's the marginal utility, diminishing marginal utility. So with the next piece of chocolate or bar that you consume, your utility is going to reduce drastically. Margin rate of substitution, MRS, the rate at which a consumer is willing to trade one good for another while maintaining the same level of satisfaction. So marginal rate of substitution is where you have the utility of good X equaling utility of good Y. If you have two goods, then we move on to graphical representation of diminishing marginal utility. The slope of indifference curve represents the MRS. A steeper slope indicates a high willingness to trade one good for another. So marginal utility functions graph is going to tell us something about the nature. Then we have real world examples, which would be cool and awesome, and we have key concepts, indifference curves, utility functions, marginal utility, marginal rate of substitution, diminishing marginal utility. Lastly, you have implication of concave indifference curve, valid the assumption, diminishing marginal utility. Okay, so these are just the summaries. We'll have more chance starting from now to get into it. I'll try to see if I get the lecture from this volume, if that is something that works. All right, let's go.
Meet the demand curve. So basically what we did actually on Friday is talk about sort of the workhorse model of economics, which is supply and demand model. And we always start the class with that because that's the model in the course. But I think as any good sort of scientist and inquisitive minds, you're probably immediately asking, well, where do these supply and demand curves come from? They're not just come out of thin air. How do we think about them? Where do they come from? And that's what we'll spend basically the first half of the course going through. And so we're going to start today with the demand curve. And the demand curve is going to come from how consumers make choices. Okay? And that will help us derive the demand curve. Then we'll turn next to the supply curve, which will come from how firms make production decisions.
So demand curve comes from consumers making choices, and supply curve comes from firms making choices. All right. Um, so I'm going to read the transcript starting from the 30th second. He says, but I think as any good shot of scientific and inquisitive minds, you're probably immediately asking, well, where do these supply and demand curves come from? That is a good question. Where do they come from? Exactly. Where do they come from? Like, do they pop up automatically, magically? Um, they don't just come out of thin air. How do we think about them? Where do they come from? And that's what we'll spend basically the first half of the course going through. So the first half of the course is going to be dissected, I think, between the demand side and the supply side. And the demand side is basically going to look like this, where individuals are making demand. So basically, essentially, people in general are making, the consumers that are coming up with the demand, and the producers are going to come up with the supply, is the essential breakdown here. And as he says, start with the demand curve, and we're going to start by taking other about people's preferences. So he's going to start going about this with people's preferences, uh, and then the utility function. So utility function is going to be second, but starting with preferences, utility functions. I have no recalling memory of what utility functions were, but I'm going to follow through now.
But let's start with the demand curve. And we're going to start by talking about people's preferences and then the utility functions. Okay? So our model of consumer decision making is going to be a model of utility maximization. That's going to be our fundamental, remember, it's of course all about constraint maximization. Our model today is going to be a model of utility maximization. And this model is going to have two components. There's going to be...
So yes, our model is all about utility maximization. Yes, utility maximization. We want to utilize, like, that is the churning of clothes, I guess. The clothes, that is the ultimate thing that we want extract out of this, which is utility maximization. And for us to maximize our utility, given the unfortunate nature of how society is organized, the scarcity of resources, and the constraints that we have on an individual level, we still want to maximize our utility. That is the fundamental property, I suppose, of this operation. So I guess budget constraints, yes, preferences and utility functions. He's going to outline this. Let him do the work.
For preferences, which is what people want, and there's going to be a budget constraint, which is what they can afford. And we're going to put these two things together. We're going to maximize people's happiness, or their choice, or their happiness given their preferences, subject to the budget constraint they face. And that's going to be the constraint maximization exercise that actually, through the magic of economics, is going to yield a demand curve.
And that's going to be the constraint maximization exercise that will actually go through the magic of economic. That when we actually go through the magic of economics is going to yield a demand curve. So this is how a demand curve is yielded. We yield a demand curve as we maximize. So yes, how we maximize our utility and preferences, rather maximize our preferences given our given our budget constraint. We maximize our preferences given our budget constraint, and through the magic of we get a demand curve. Demand curve.
A very sensible demand curve that you'll understand intuitively. Now, so what we're going to do is do this in 3 steps. Step 1 over the next 2 lectures. Step 1 is we'll talk about preferences. How do we model people's tastes? We'll do that today. Step 2 is we'll talk about how we translate this to utility function, how we mathematically represent people's preferences in the.
So utility function again. So he starts with preference again. He as you can see, he has just 2. I think this is utility maximization. He's talking about utility maximization. Utility maximization is basically utility maximization should have utility function. He adjusts that by utility functions. Any case, I think that's not going to be an issue. So again, he addresses that he is going to talk about preference and budget constraints, and we have the preference thing here. How do people, how is like how do they come about their tastes, and how do they develop their tastes, which is their preferences, and the mathematical version of their preference is the utility function. Utility function gives you the mathematical representation for that. And then you have number 3, which is budget constraint, and not subject to today's lecture.
Function. We'll do that today as well. And then next time, we'll talk about the budget constraints that people face. So today we're going to talk about the max demand. Next time we'll talk about the budget constraint. That means today's lecture is quite fun. Today's lecture is about unconstrained choice. We're not going to worry all about what you can afford, what anything costs. Well, worry about what things cost. We're not going to worry what you can afford. Okay? Today is the lecture where you won the lottery. Okay? You won the lottery. Money is no object. How do you think about what you want? Okay? Next time we'll say, well, you win the lottery. In fact, it's one late in the semester, no one wins the lottery. That's an incredibly bad deal. But basically, next time we'll impose the budget constraints. But for today, we're just going to ignore that and talk about what do you want. Okay? And to start this, we're going to start with a series of preference assumptions. A series, remember, as I talked about last time, models rely on simplifying assumptions. Otherwise, we could never write down a model. It would go on forever. Okay? And the key question is, are those simplifying assumptions sensible? Do they do violence to reality in a way which makes you not believe the model? Or I want to start with
I'm going to skip through this portion, preference assumptions and non-saturation assumptions, and go straight to indifference curves and see what's that about. So apparently what we're getting is graphical representation of consumer preferences. Graphical representation of consumers' preferences. Yeah, okay, so the the preference, the mathematical one is utility functions, I guess. Yes, functions. So utility functions are going to be preference, utility function, and indifference curve. Two things. Preference is going to be mathematical. Preference could have 2 outlooks or outputs. Preference could be of 2 types and could be viewed or understood or thought of as 2 distinct things. One could be a mathematical model, which is the utility function, my understanding at least, and the second one is a graphical format, which is going to be the indifference curve. Let's see.
Graphical representation of preferences. I want to graphically represent people's preferences. And I'll do so through something we call indifference curves. Indifference curves. Okay? Indifference curves are basically preference maps. Essentially, indifference curves are graphical maps of preferences. Okay? So, for example, suppose your parents gave you some money at the beginning of the semester, and you spend that money on 2 things. Your parents are rich, they give you tons of money. Spend that money on 2 things: buying pizza or eating cookies. Okay? So consider preferences between pizza and cookies. That's the 2 things you can do. Once again, it's an extreme model. Obviously, in life, you can do a million things with your money. But it turns out, if we consider the contrast between doing 2 different things with your money, you get a rich set of intuition that you can apply to a much more multidimensional decision case. So let's start with a 2-dimensional decision case. You've got your money, you're going to have pizza or you're going to have cookies. Okay? Now consider 3 choices. Okay? Choice A is 2 pizzas and 1 cookie. Choice B is 1 pizza and 2 cookies. And choice C is 2 pizzas, 2 cookies. Okay, that's the 3 packages I want to compare. And I'm going to assume, and I'll mathematically rationalize in a few minutes, but for now I'm going to assume you are indifferent between these two packages. I'm going to assume you're equally happy with 2 slices of pizza and 1 cookie, or 2 cookies and 1 slice of pizza. Okay? I'm going to assume that. But I'm also going to assume you prefer option C to both of these. In fact, I'm going to assume that because that is what more is better gives you. Okay? So you're different between these. This indifference doesn't come from any property I wrote about. That's an assumption. That's just for this case, I'm assuming that. This comes from the third property I wrote up there. You prefer package C because more is always better than less. Okay? So now, let's graph your preferences. And we do so in figure 2.1. Okay, the handout. Here's your indifference curve. So we graphed on the x-axis your number of...
So indifference curves are shaped like this, like they are curvy, curves, indifferent curves. By definition, they're curvy, and basically it's saying that people are all right with any combination here and here.
Number of cookies on the y-axis, slice of pizza. Okay? Now, we've graphed the 3 choices I laid here. Choice A, which is 2 slices of pizza and 1 cookie. Choice B, which is 2 cookies and 1 slice of pizza. And choice C, which is 2 of both. And I've drawn on this graph your indifference curves. The way your indifference curve looks is there's one indifference curve between A and B, because those are the points among which you're indifferent. So an indifference curve represents is all combinations of consumption among which you are indifferent. That's why we call it indifference curve. So a difference curve, which will be sort of one of the big workhorses of this course.
So it's crucial because think of it like this. It is an indifferent curve. I don't think so because of the following reason. So this one is going to cost you 15, this one is going to cost you 12, and this one is going to cost you 7 only. So this is not the right indifferent curve. The indifferent curve would be like this, like, would it be? Not very a good point, because this is like considering only one product or good, and here we are considering 2 products or goods. So
represents all combinations along which you are indifferent. You are indifferent between A and B, therefore they lie on the same curve. Okay? So that's sort of our preference map, our indifference curves. And these indifference curves are going to have 4 properties. 4 properties that you have to, that follow naturally from this. That's really 3.5. The third and fourth are really pretty much the same, but I like to write them out as 4. 4 properties that follow from these underlying assumptions. Property 1 is consumers prefer higher indifference curves. Consumers prefer higher indifference curves. Okay? And that just follows from more is better. That is an indifference curve that's higher goes to a package that has at least as much of one thing and more of the other thing. Therefore, you prefer it. Okay? So as indifference curves shift out, people are happier. Okay? So in that higher indifference curve, point C, you are happier than points A and B because more is better. Okay? The second is that indifference curves never cross. Indifference curves never cross. Okay, actually, that's third, actually. I want to come to that in order. Third is indifference curves. Second is indifference curves are downward sloping. Second, indifference curves are downward sloping. Okay, indifference curves are downward sloping. Let's talk about that first. Okay? That simply comes from the principle of non-satiation. So look at figure 2.2. Here's an upward sloping indifference curve.
So remember that indifference curves is our way of getting to demand curves. So we're starting with indifferent curves, and because demand curves are downward sloping, indifference curves are going to be downward sloping as well. And upward sloping indifferent curve, as mentioned here, might not make sense, but let's check that out anyway.
Okay, why does that violate the principle of non-satiation? Why does that violate that? Yeah.
Either you're less happy if you have more cookies, or you're less happy if you have more pizza.
Yeah.
I mean, there's, and that violates non-satiation.
Exactly. So basically, you're indifferent. On this curve, you're indifferent in 1 of each and 2 of each. You can't be indifferent. 2 of each has got to be better than 1 of each. So an upward sloping indifference curve would violate non-satiation.
Yeah. Two of this would be better than 1 of this. This makes absolute more sense, because more is always good. So this is the principle of non-satiation. So when we say that demand curve is upward sloping, downward sloping, this is exactly what we mean. For instance, if we have 2 goods and the demand curve is upward sloping as opposed to downward sloping, we are essentially saying that we would be it would violate some form of principle, but it is more clear to see with the indifference curve here, because indifference curves precede demand curves, and that's why they are downward sloping. It has to be downward sloping, because when we have downward sloping, we have a good distribution. For instance, this goes up and this goes up, and this way is the zero portion. So when we have downward, we have the right amount of, like, the lowest point basically gives you 0, and the higher you go you have the distribution adjustment, appropriate distribution adjustment basically.
The second property of a difference curve. The third property of a difference curves never cross. Okay? We can see that in figure 2.3. Okay? Someone else tell me why this violates the properties I wrote up there in difference curves crossing. Yeah? What's that? Because the B and C, B is strictly better, that's right. But they're also both on the same curve as A. So you're saying you're indifferent with A for both B and C, but you can't be because B is strictly better than C. So it violates transitivity. Okay? So the problem with crossing difference curves, they violate transitivity. And then finally, the fourth is sort of a cute extra assumption, but I think it's important to clarify, which is that there is only one indifference curve through every possible consumption bundle. Only one IC through every bundle.
Understandable.
Okay, you can't have two indifference
Like
curves
they
going through the same
cannot
bundle.
cross,
Okay,
and like
and that's because of completeness. If you have two indifference curves going through the same bundle, you wouldn't know how you felt. Okay, so there can only be one going through every bundle because you know how you feel. You may feel indifferent, but you know how you feel. You can't say I don't know. Okay, so that's sort of an extra assumption sort of completes the link to the properties. Okay, so that's basically how indifference curves work. Now, I find when I took this course before you were, God, maybe before your parents were born, I don't know, certainly before you guys were born. Okay, when I took this course, I found this course full of a lot of light bulb moments. That is, stuff was just sort of confusing, and then boom, an example really made it work for me. And the example that made a difference curves work to me was actually during my first Euro. When my Euro was with a grad student, and that grad student had to decide where he was going to accept the job. He had a series of job offers, he had to decide. And basically said, here's the way I'm thinking about it. I'm indifferent, I have a difference map, I care about two things. I care about school location, and I care about economics department quality. Okay, I care about the quality of my colleagues and the research that's done there and the location. And basically, he had two offers. One was from Princeton, which he put up here, no offense to New Jerseyans, but Princeton as a young single person sucks. Okay, fine when you're married and have kids, but deadly as a young single person. And the other, so that's Princeton. Down here was Santa Cruz. Okay, awesome, Canada's most beautiful university in America. Okay, but not as good in the economics department. And he decided he was roughly indifferent between the two. But he had a third offer from the IMF, which is a research institution in DC, which has he had a lot of good colleagues, and DC is way better than Princeton, New Jersey, even if it's not as good as Santa Cruz. So he decided he would take the offer of the IMF. Okay, even though the IMF had worse colleagues than Princeton, and worse location than Santa Cruz, it was still better in combination of the two of them, given his preferences. And that's how he used indifference curves to make his decision. Okay? So that's sort of an example of applying. Once again, no offense to the New
that is a nice trick.
in the room, of which I'm one, but believe me, rather than Santa Cruz. Okay, so now let's go from preferences to utility functions. Okay, so now we're moving from preferences.
Utility function, that was the second thing. Preference to function. So this is like where he is heading towards. The issue is, these should be essentially the same thing. One is mathematical, the other one is graphical. Other than that, it shouldn't be different. But let's check this out, see what this is.
Which we represent graphically to utility functions, which we're going to represent mathematically. Remember, I want you to understand everything in this course at three levels: graphically, mathematically, and most importantly, all intuitively. Okay? So graphic is indifference curves. Now we come to mathematical representation, which is utility function. Okay? And the idea is that every individual, all of you in this room, have a stable, well-behaved, underlying mathematical representation of your preferences, which we call utility function. Okay? Now, once again, that's very complicated. Your preferences over lots of different things. We're going to make things simple by writing down two-dimensional representation for now of your indifference curve. We're going to say, how do we mathematically represent your feelings about pizza versus cookies? Okay? Imagine that's all you care about in the world is pizza and cookies. How do we mathematically represent that? So, for example, we could write down that your utility function is equal to the square root of the number of slices of pizza times the number of cookies. We could write that down. I'm not saying that's right. I'm not saying it works for anyone in this room or for everyone in this room. But that is a possible way to represent.
There are different types of utility functions. What are some of the most So I recall this much because different utility functions could have different names and they could look different, and they would be useful through calculus. So there was this one person, I'm forgetting his name, Luke something. I don't recall, but he had a playlist in which he dealt with the mathematical aspect of this demand functions. So the first one is Cobb-Douglas. Cobb-Douglas, his utility comes from x and y, two variables or parameters. So it's basically x times a and y times b. X powered by a times y powered by b. What would that be? quantity of two goods, A and B positive constants and represented relative importance of two goods. Okay. Widely used due to flexibility and realistic properties, exhibits diminishing marginal utility. The more you have of good A, the extra less satisfaction you get from consuming even more of it. I don't understand. Implies the consumers like variety. Okay. Perfect substitution utility function. Perfect substitutes the utility function ax plus by. A, x and y represent the quantity of two goods. A and b are positive constants that represent the utility gained from each unit x and y respective. I have to delve a bit deeper and get some examples out of this. Characteristics: goods are perfectly interchangeable. The consumer is indifferent between consumer one and slightly less. Okay. Perfect complement utility is ax plus b, ax comma by are positive constants. Okay. Linear utility function, it doesn't have a name, ax plus by. Just the utility function seems like the same function as the demand curve, just linear. Demand curve seems to be a linear, quasi-linear. You have f of x plus by and fx is a function. Important notes. Critique easy to understand. Hopefully they come up with okay, yes. Cobb Douglas. Imagine you like both apples and oranges, but you don't like either one too much or more than the other. A Cobb Douglas utility function would represent this. It means you get some satisfaction from each, and having a mix is better than having it done of just one. For example, having three apples and two oranges gives you a certain level of satisfaction. Having five apples and one oranges might give you a roughly the same satisfaction depending on the specific correspondent exponent of Cobb Douglas equation. You wouldn't be much happier with 10 apples and one oranges, showing diminishing return. Just think. Okay, let's just reread this. Cobb Douglas utility might be this. This means your value pizza is slightly more than movies because the exponent of pizza is higher. Okay, example 3m. This is not going to work out. We're going to have to do more later. I hope it did not reveal much. Could have revealed much. Who knows? Who cares?
Utility. Okay? What this would say, this is convenient. We'll end up using square root form a lot for utility functions, a lot of convenient mathematical properties. And it happens to jive with our example, right? Because in this example, you're different between two pizza and one cookie, or one pizza and two cookies. They're both square root of 2. And you prefer.
Okay, I think I'm going to take a slight pause and just resume this afterward. Pause. Okay, we are back, and let me just get rid of this. Okay. So, by the way, this sounds, but this seems like a Cobb Douglas function of a kind.
Pizza and two cookies, that's 2. Okay? So this gives you a high utility for 2 pizza and 2 cookies. Okay? Then one pizza and 2 cookie, or 2 pizza and 1 cookie. So now the question is, what does this mean? What is utility? Okay? Well, utility doesn't actually mean anything. There's not really a thing out there called utils. Okay? In other words, utility is not a cardinal concept. It is only an ordinal concept. You cannot say your utility, you cannot literally say my utility is X% higher than your utility, but you can rank them. So we're going to assume that utility can be ranked to allow you to rank choices. Even if generally we might slip some and sort of pretend utility is cardinal for some cute examples, but by and large, we're going to think of utility as purely ordinal. It's just a way to rank your choices. It's just when you have a set of choices out there over many dimensions. Like if your choice in life was always over one dimension, and more was better, it would always be easy to rank it, right? You never have a problem. Once your choice over more than one dimension, now if you want to rank them, you need some way to combine them. That's what this function does. It allows you essentially to weight the different elements of your consumption bundle, so you can rank them when it comes time to choose. Okay? Now this is obviously incredibly simple, but it's
So this is a good way of putting it as well. For instance, we've seen different formulas or different versions of this. Yes, this. So Cobb Douglas is basically this, and we have this is essentially saying that we have two dimensions. You could either have pizza or you could either have burger or whatever. And once you have two dimension, what you need to do is the relationship of your preference is kind of subject to weighting, like how much weight do you put on one thing as opposed to other, because now things happen in combination, it doesn't happen in isolation, or it's basically having two different variables. Dimension might be a bit too complex of a term to digest, but it just happens to have two variables and you have to make decisions of the combination of those two variables.
be amazingly powerful in explaining real world behavior. Okay? And so what I want to do today is work with the underlying mathematics of utility, and then we'll come back and see in the next few lectures how it can actually be used to explain decisions. So a key concept we're going to talk about in this class is margin utility. Margin utility is just a derivative of the utility function with respect to one of the elements. So the margin utility for cookies is utility of the next cookie, given how many cookies you with respect to one of the elements.
So marginal utility is the utility function with respect to one of the cookies. So makes sense first of all that we have a curvy function and we can take a derivative and that will just give a straight line. So makes sense.
Margin utility for cookies is utility of the next cookie, given how many cookies you've had. This class can be very focused on marginal decision making. In economics, it's all about how you think about the next unit. Turns out that makes life a ton easier. Turns out it's way easier to say, do you want the next cookie, than to say, how many cookies do you want? Because if you want the next cookie, that's sort of a very...
So again, this is like fundamental key insight. Like it is very easy to... It's slightly easier to ask you, do you want another cookie, than how many cookies do you want? Like if you eat one, that might be enough. It could be something that is not... something you don't find particularly tasty, so you might not be having more than one or even one entirely. So you're so the next one do you want is an easier question in general than to ask like how many do you want.
Isolated decision. You say, okay, I've had this many cookies, do I want the next cookie? Whereas before you start eating, you say how many cookies
With
do you want? That's
respect
sort
to
of a harder, more
decision
global
making.
So we're going to focus on the stepwise decision-making process of do you want the next unit, the next cookie, or the next slice of pizza? Okay? And the key feature of utility functions we'll work with throughout the semester is that they will feature diminishing margin utility. Margin utility will fall as you have more of a good. The more of a good you've had, the less happiness you'll derive from the next unit. Okay? Now we can see that graphically in figure 2.4. Figure 2.4 graphs on the x-axis the number of cookies holding constant pizza. So let's say I have 2 pizza slices, and you want to say, what's my benefit from the next cookie? And on the left axis, violating what I just said like 15 seconds ago, we graph utility. Now once again, the util numbers don't mean anything, it's just to give you an ordinal sense.
It's like, does it do anything if I do this, or just... All right. What happens? What other gestures can we do? Like, sure. Okay, nice. Good. Does it do a heart? Holy shit, it does. This is good. This is good. We'll have to move on. Diminishing marginal utility. So this function, a few interesting things to observe about this function is that the graph of root is always going to be downward sloping like this. So that is one observation. Number two is it outlines what happens when we have another unit of the same good. it just goes down like this. Like the first one, yes, we want to consume more, but as we consume, keep consuming, it just goes downward, downward, and downward. So these are two good observations to have just at looking at the um, graph.
What you see here is that if you have one cookie, your utility is 1.4, square root of 2 times 1. If you have two cookies, your utility goes up to square root of 4, which is 2. You are happier with two cookies, but you are less happy from the second cookie than the first cookie. Okay? And you can see that in figure, if you flip back and forth between 2, 4, and 2, 5, you can see that. Okay? The first cookie, going from 0 to 1 cookie, gave you 1. So in this case, we're now graphing the marginal utility. So figure 2, 4 is the level of utility, which is not really something you can measure, in fact. Figure 2, 5 is something you can measure, which is marginal utility. What's your happiness? We'll talk about measuring this. From the next cookie. You see, the first cookie gives you a utility increment of 1.4. Okay? You go from utility of 0 to utility of 1.4. The next cookie gives utility increment of 0.59. Okay, you go from utility of 1.41 to utility of 2. The next cookie gives utility increment of 0.45, the square root of 3. So now we flip back to the previous page. We're going from the square root of 4 to the square root of 6. Square root of 6 is only 0.45 more than the square root of 4, and so on. So each additional cookie makes you less and less happy. It makes you happier. It has to, because more is better. But it makes you less and less happy. Okay? And this makes sense. Just think about any decision in life starting with nothing of something and having the first one, slice of pizza, a cookie, deciding which movie to go to. The first movie, the one you want to see the most, okay, is going to make you happier than the one you want to see not quite as much. The first cookie, when you're hungry, will make you happier than the second cookie. The first slice of pizza will make you happier. Now, you may be close to indifferent. The second slice of pizza makes you almost as happy as the first. But the first will make you happier. Okay, if you think about it, that's really sort of that first step. You were hungry, and that first one makes you feel happier. Now, but you got to remember, you always want more cookies. Now, you might say, wait a second, this is stupid. Okay, once I've had 10 cookies, I'm going to barf. The 11th cookie can actually make me worse off because I don't like barfing. But in economics, we have to remember, you don't have to eat the 11th cookie. You can give it away. So if I say you want the 11th cookie, you can save it for later. You can give it to a friend. So you always want it. In the worst case, you throw it out. It can't make you worse off. It can only make you better off. And that's where sort of more is better assumption comes from. Obviously, in the limit, if you got a million cookies, your garbage can gets full, you have no friends to give them to. I understand the limit, these things fall apart. Okay? But that's the basic idea of more is better and the basic idea of diminishing margin utility. Okay, any questions about that? Yeah.
Diminishing margin.
Utility function can never be negative because we have, well, utility is not an ordinal concept. You can set up utility function such that the number is negative. You can set that up. Okay, the margin utility is always positive. You always get some benefit from the next unit. Utility, once again, the measurements are relevant, so you can be negative, you can set it up, I can write my utility.
Marginal utility is always going to be positive. Is there a rule that when we take a derivative of something negative, it just turns into positive? Is there a rule? No, I suppose no.
Like this, something like that. So it can be negative, that's just a sort of scaling factor. But marginal utility is always positive. You're always happier, or it's non-negative. You're always happier, or at least indifferent to get the next unit. Yeah?
So when you're looking at why do you get a definition of the
Starting from 1. So now, let's flip back from the math to the graphics and talk about where indifference curves come from. I just drew them out. But in fact, indifference curves are the graphical representation of what comes out of utility function. Okay? And indeed,
that is a key piece of information, that utility functions, indifferent curves, are basically the graphical form that comes out when you draw out the mathematical function.
Slope of the indifference curve, we're going to call the marginal rate of substitution. The rate essentially at which you're willing to substitute one good for the other. The rate
slope of the indifference curve, how do we get that? We get that from taking a derivative. Slope of the marginal rate of substitution is going to be just the derivative. That is the slope, diminishing margin. So what is marginal utility is going to be the derivative of the utility function, right? And then the slope of the, that might be confusing.
To substitute cookies for pizza is your marginal rate of substitution. And we'll define that as the slope of the indifference curve, delta P over delta C. That is your marginal rate of substitution. Literally, the difference curve tells you the rate you're willing to substitute. You just follow along and say, look, I'm willing to give up. So in other words, if you look at figure 2.6, you say, look, I'm indifferent between point A and point B. One slice of pizza, one cookie and 4 slices of pizza is the same to me as 2 cookies and 2 slices of pizza. Why is it the same? Because they both give me utility square root of 4, right? So given this mathematical, I'm not saying you are, I'm saying given this mathematical representation, okay, you are indifferent between point A and point B. So what that says, and what's the slope of the indifference curve? What's the arc slope between point A and point B? The slope is negative 2. So your marginal rate of substitution is negative 2. You are indifferent. Okay, you're indifferent between 1, 4, and 2, 2. Therefore, you're willing to substitute or give away 2 slices of pizza to get 1 cookie. Delta P, delta C is negative 2. Okay? Now, it turns out you can define the marginal rate of substitution for any segment of a difference curve. And what's interesting is it changes. It diminishes. Look what happens when we move from 2 pizzas and 2 cookies from point B to point C. Now the marginal rate of substitution is only negative 1/2. Now I'm only willing to give up 1 slice of pizza to get 2 cookies. What's happened? First, I was willing to give up 2 slices of pizza to get 1 cookie. Now I'm willing to give up 1 slice of pizza to get 2 cookies. What's happened? Yeah. Because of? Exactly. diminishing marginal utility has caused the marginal rate of substitution itself to diminish. For those of you who are really kind of better at math than I am, it turns out technically, mathematically, marginal utility isn't always diminishing. You can draw cases. MRS is always diminishing. So you can think of marginal utility as always diminishing. It's fine for this class. When you get to higher level math and economics, you'll see marginal utility doesn't have to diminish. MRS has to diminish. Okay, MRS is always diminishing. As you go along the indifference curve, that slope is always falling. Okay? So basically, what we can write now is how the MRS relates to utility function. Our first sort of mind-blowing result is that the MRS is equal to the negative of the marginal utility of cookies over the marginal utility of pizza. That's our first key definition. It's equal to
Did I get this? Absolutely not.
marginal utility of cookies over the marginal utility of pizza.
Although this is going to be my third or fourth time, who knows, studying this, but this is confusing. Marginal rate of substitution is basically, there has to be a better definition. Price of pizza consumption, is it like price and consumption? And what is like marginal utility of, let's just follow through.
That's our first key definition. It's equal to the negative of the marginal utility of the good on the x-axis over the marginal utility of the good on the y-axis. Okay? Essentially, the marginal rate of substitution tells you how your relative marginal utilities evolve as you move down the indifference curve. When you start at point A, you have lots of pizza and not a lot of cookies. When you have lots of pizza, your marginal utility is small. Here's the key insight. This is the thing which, once again, it's a light bulb thing. If you get this, it'll make your life so much easier. Marginal utilities are negative functions of quantity. The more you have of a thing, the less you want the next unit of it. That's why, for example, cookies is now the numerator and pizza is the denominator. Flipping from this side. Okay? The more you have the good, the less you want it. So start at point A. You have lots of pizza and not a lot of cookies. You don't really want more pizza. You want more cookies. That means the denominator is small. The marginal utility of pizza is small. You don't really want it. But the marginal utility of cookies is high. You don't have many of them. So this is a big number. Now let's move to point B. And think about your next decision. Well, now, your marginal utility of pizza, if you're going to go from 2 to 1 slice of pizza, now pizza's worth a lot more than cookies. So now it gets smaller. So essentially, as you move along that indifference curve, because of this, because diminishing marginal utility, it leads to this issue of a diminishing marginal rate of substitution. Okay? So basically, as you move along the indifference curve, you're more and more willing to give up the good on the x-axis to get the good on the y-axis. As you move from the upper left to the lower right on that indifference map, figure 2.6, you're more willing to give up the good on the x-axis to get the good on the y-axis. And what this implies is that indifference curves are convex to the origin. Indifference curves are convex to the origin. It's very important. Okay, let's see. They are not concave. They're either convex or straight. Let's say they're not concave to the origin. Okay, to be technical. Indifference curves can be linear. We'll come to that. But they can't be concave to the origin. Why? Well, let's look at the next figure, the last figure, figure 2.7. What would happen if indifference curves were concave to the origin? Then that would say moving from one pizza. So now I've drawn a concave indifference curve. And with this indifference curve, moving from point A to point B leaves you indifference. So you're happy to give up one slice of pizza to get one cookie. Starting with 4 slices of pizza and 1 cookie, you are happy to give up 1 slice of pizza to get 1 cookie. Now, starting from 2 and 3, you're now willing to give up 2 slices of pizza to get 1 cookie. What does that violate? Why does that not make sense? Yeah. Yeah, law of diminishing marginal utility. Here, you were happy to have 1 slice of pizza to get 1 cookie. Now you have 2 slices of pizza to get 1 cookie, even though you have less pizza and more cookies. That can't be right. As you have less pizza and more cookies, pizza should become more valuable, not less valuable. And cookies should become less valuable, not more valuable. So a concave to the origin indifference curve would violate the principle of diminishing marginal utility, diminishing marginal rate of substitution. Okay? Yeah.
What if, like, my trading card?
Okay.
Like, if you can, I mean, I'd get more trading cards.
But that is what's one cards. Think about how you properly model addictive decisions like smoking. And addictive decisions like smoking, essentially, it really is that your utility function itself shifts as you get more addictive. It's not that your marginal utility, the next cigarette's still worth less than the first cigarette. It's just that as you get more addicted, that first cigarette gets worth more and more to you. So when you wake up in the morning feeling crappy, that first cigarette still does more for you than the second cigarette. It's just the next day you wake up feeling crappier. Okay? So we model addiction as something where essentially each day, cigarettes do less and less for you. You get essentially adjusted to you get habituated to higher levels. And this is why I do a lot of work, this is why, unfortunately, we saw last year the highest number of deaths from accidental overdose in U.S. history. 72,000 people died from drug overdose.
Okay, I think we are going to wrap this up with trying to wrap our heads around marginal rate of substitution, MRS, the rate at which a consumer is willing to trade one good for another while maintaining the same level of satisfaction. Okay, so marginal MRS, marginal rate of substitution, is basically a rate at which two things have the same utility, and for two things to have the same utility, you have to, like, where's the formula? I need to get back to the formula. So essentially means that marginal I'm absolutely confused about like what is this? Like this is marginal utility of C and marginal utility of cookie and pizza. I get that. What I don't get is like what is this change in P? Oh, change in P is going to be just the x-axis. Like change in the quantity. This is like quantity. This is alluding to quantity, and this is alluding to uh, some relation of how much quantity do we want. Like this is like modeling preferences. We go about it. Nice, I understand it now. So the what it's going to simplify into is change in pizza times the marginal utility of pizza is going to be the negative change in cookies times the marginal utility of cookies. So what we are going to have is the change in, so they have the same collective, so marginal rate of substitution is the key part. Substitution is the absolutely key part. What we have is trying to show, what we are going to have is this. Is it like feasible or is it like distorted? So this is the rate of change of pizza and this is the marginal utility of pizza is going to equal to the negative of, forget the negative for a minute, but change in cookies, how much cookie we consumed times the marginal utility of cookies. So what marginal rate of substitution is telling us is that they would have the same marginal utility. That is the only thing that we have to contend with or understand. I think I'm kind of have a hold of it right now. Diminishing as the consumer consumes more of a good, marginal rate of substitution diminishes as consumer consume more of one good. Yes, it does. This particular line, like yes, it does. And as it does, it basically lowers the demand curve. So I guess this is why marginal rate of substitution is the reason why we have downward sloping demand curve. This is probably the ideal message or the key message that this particular line is sending. That is my understanding. Next, we have graphical representation of diminishing marginal utility. The slope of the indifference curve represents the marginal rate of substitution. Slope of the indifference curve. I thought the slope of the indifference curve was the marginal rate of. Oh, right. Makes. I think it just clicked for me. So what we have is like, sure, I can write, I can draw. Why not? Is there? Yes, I can draw. I can draw and I will draw. So what we have is like we just saw that we had one sort of utility function. We thought that this was the utility function. But utility function could take different shapes. For instance, it could be straight line, it could be that line, it could be this line. So what we assume that when we're confused about this one, right? So what is the marginal rate of utility for C, which is cookie? What is the marginal rate of utility for pizza? We understand the change in P. So change in P might be like going from this place to like that place, like this place to that place, right? We understand this. This is like change in, if this is P, change in P. Change, okay, good lord. This is like change in P. Change in P, all right? So we are assuming that how would we, this is the indifference curve basically. This is the indifference curve. How the hell do I write that? Indifference curve, I and D. Indifference curve and oh good lord, indifference curve, and this is like the marginal rate of substitution. This is absolutely that marginal rate of substitution. But what we're trying to understand is like how did these two things come about, and they come about when you have different utility functions. So for instance, the utility function of pizza could be a perfect substitution utility function, so that would result in this formula. Yes, this formula, like 2c plus 2pe, right? So this is the perfect substitution model, and once we take a derivative of this particular thing, we get this particular um, value. And this number in the bottom could be a Cobb Douglas, it could be anything, it could be a linear function, and we can take that derivative from here. And to get the marginal rate of substitution mathematically without the help of this, just through numbers, we'll have change in p. For instance, this is the change in p, and if we are considering this place to this place, this would be change in q, this would be change in q. And we have the derivative version. If the formulas are given, we can get the derivatives of this, we can also get the derivative of this, and then we have marginal rate of substitution. Voila. How do we stop recording? Stop recording.